last time, we have sort of solved this general discrete-time LQ optimal control problem. Okay? We have sort of explained how to take partial derivatives for matrix, and later we talked about how to move from the general optimization problem to discrete-time LQ optimal control problem. I want to start with a review, writing down of the central equations for LQ, discrete-time LQ problem. Okay? This set of equations, you have to write it down once along the course of taking this ME233. So when you write it, you understand more about it. So review of discrete-time LQ solution. So we have a system. So in this case, I will use the time invariant system just for simplification of writing. Xk plus 1 equals A, Xk plus BUK. Okay? And our performance index, so you probably are becoming very familiar with this, is the terminal cost plus a sequence of cost along the path. Let's say we start at K0. So I'm going to have X transpose K, Q, Xk plus U transpose K, RUK. Okay, this is a performance index. From time to time, we often write this Q here as C transpose C. Okay, this is just for convenience, because if we write it this way, now think about this product term. We're going to have X transpose C transpose times C transpose X. So it's sort of like equivalent to CX transpose CX. Because we often in linear systems, we often write it like this: Y equals CX. So it's sort of like we are minimizing the output of the system. Okay, so that's just a common way of writing Q. Huh?
If we want to minimize Y, we should put C transpose C. Otherwise, we should select another Q. Is that right?
Can you repeat the question?
If we want to minimize Y, we should put Q equals to C transpose C.
Mm-hmm.
Otherwise, we should select another Q.
Yes, yes, yes. So a student asked that we can select this Q different from the system matrix as well if we want to minimize something else. Okay, that's totally feasible as well. Okay, so the optimal control law is this: U optimal at each time index equal to negative. This is what I usually do. I write down the structure first, and then I fill in the blanks. It's a state feedback control law, okay? And above here are a bunch of matrices that we derived last time. Okay? And the optimal cost, J optimal at time 0, is going to be a quadratic function of the initial state times P0 times X0. Okay? So state feedback law, optimal is a quadratic function of the initial state. Okay? Last time we derived the Riccati equations for this P. I won't repeat it again here. Okay? This is what we discovered last time. Okay? We said that for this Riccati equation, we found out if we initialized this boundary condition at several, we chose multiple initial conditions for this Pn over here. And then in the end, we found the solution just always converges to these steady state solutions. All right? Now, if you think about what you learned in ME 232, do you remember any assumptions for a steady state solution to exist? For these convergence, there are conditions the system has to satisfy. Someone said stability. Someone said stability. That's closer, not perfect answer. Any other? Controllability. Any other guesses? Now you're just guessing random. No, that's controllability. So if you review in ME 232, these are the assumptions for a steady state LQ problem to exist. AB pair has to be controllable or stabilizable. And the AC pair has to be observable or detectable. Okay? So these two conditions are for different situations to occur. Okay? The controllability is for this one to converge. So for the observability condition, it's not related to the convergence of the Riccati equation. That's for something else. Okay? So in this lecture, I want to dig into some more details about this aspect. This aspect may not be written on the class reader, which you will purchase later. But I want you to be able to understand why these conditions are needed, and specifically, what are the purposes for each one of them. Okay? So here is a short summary. Let me hide this first. Here is a short summary of what I just talked about. For this Riccati equation with boundary condition like this, it turns out in the case of limiting this limiting this optimization frame to be infinity, if AB is controllable or stabilizable, then it's guaranteed this Riccati equation is going to converge to a bounded matrix in the steady state. Okay? This is regardless of how you assign the initial values. Okay? And that's kind of nice because it tells us we can converge to a constant matrix. Then when we implement the control law, we can simplify the design, we simplify the computation. Okay? Now, I want you to understand this is sort of intuitive in some sense. Okay? Remember, we are doing this minimization problem, okay, which is a quadratic function of x and u. If the system is not even controllable or stabilizable, think about what will happen. It means some of the states we cannot control, right? So it's largely possible these states have chances to blow up to infinity, right? That's the intuitive meaning of not controllable or not stabilizable, right? So if some of the states just go wild, this guy is going to go to infinity. We can't minimize it. We don't have the control effort to place on these states, right? Now, I just told you, we just reviewed this. The optimal cost is a quadratic function of this. Now, if this is infinity, and we started with some finite initial conditions, then it has to be the case that this guy is going to have an infinity norm. Its norm of this matrix is going to be infinity. All right? Make sense? So this is what I will do when talking about these kind of things. I'll first give it the intuition, and then I will guide you through the mathematic details. Okay. I'll start with this one then. Okay? So now we've talked about this convergence of the Riccati equation. Now, if the Riccati equation is going to converge, it's going to converge to this algebraic Riccati equation, ARE. Sometimes we write it as ARE. Okay? So we just have to solve this equation, which sort of looks like a quadratic equation of P, right? Okay. If this is convergent, then it means our control law converges to a constant matrix, constant state feedback control law. These are constant matrices. Okay? Then it turns out it's convenient to define the cost in this way. Okay? Well, what's the difference of this one compared to the cost we introduced earlier? This cost here. We don't have, yeah, someone else wanted to say something? We don't have the final terminal cost, right? And the idea behind this is sort of intuitive. If we're going to do this control design, when we want to minimize this, then in the end, x has to converge to 0, right? It doesn't make much sense if I want to minimize this and then in the end it doesn't converge to 0, right? It turns out, under the controllability, observability conditions, we can guarantee they will converge to 0. Not necessary to include the terminal cost. And that's a fantastic feature of this LQ problem. Okay? So let me read it to you. This is sort of a wrap-up of what we discussed. Controllability condition, observability condition with this definition of Q. We can have guaranteed closed-loop asymptotic stability for this one, which is meaning x will converge to 0 asymptotically. Okay? So I defined over here, I made some new definitions here. This equation comes from this. So xk plus 1, this comes from axk plus buk, and then I just substitute in uk equals negative kx xk, all right? Optimal control law is a state feedback control law, so I just plug it in here, I get this a minus bk. And then I defined this matrix, a minus bk, as a closed loop matrix, okay? First of all, we have seen this. Controllability means PS and KS is going to be bounded, right? We have just shown this. We have shown the intuition of this. Now, the tricky part, mathematically tricky part, is this observability condition. The observability condition is going to guarantee us we're going to have the matrix P of S is going to be positive definite if it's, the system is observable, okay, with this optimal control law and this definition of Q, okay? Again, I'll start with some intuition for this condition first, and then we'll dig into the mathematic details, okay? The intuition is like this. Remember, we have this cost function, infinity, let's say. Xk, so let's say this is summation k. R uk. So we have sort of seen the controllability condition means we can control the states. So the final cost is going to be finite, all right? And the observability condition is kind of makes sense in this way. If the system is observable, it means we can see how the system is going on from the states, from this cost, right? The meaning of observability means from the output measurement. I've told you if Q is defined as C transpose C, then this whole term looks like Y transpose K, Y transpose K times YK for this term, right? I have explained to you that if the system is observable, then it's sort of intuitive that we can see how the states are going on from the output. That's the intuitive definition of observability. We can see how the system is going on from the output, all right? Now, if you buy that, then this makes sense, right? If we can see how the states are going on from the output intuitively, then if we are minimizing this, it's intuitive to say that the closed-loop system will be controlled to be stable, right? We'll dig into some more details about that. Okay, the first the first step to show this observability implies P is positive, definite, is to do one step in the cost function. Okay, is to restructure this this performance index in sort of a little bit different way. You remember that this U, this optimal control law, is negative kx times xk, right? If you plug in this one here, then you're going to see this cost is nothing but one quadratic function of x, another quadratic function of x. So you can massage these two terms together. So it's going to be a big quadratic function of x over here. And the inside, this matrix is slightly different. So it's a combination of these first two. It comes from these ways. So first of all, substitute Q to be equal to C transpose C. Then I'm going to have one term, X transpose times C transpose times C. So this is the first term. And then the second term comes from over here. This matrix occurs like this. From this substitute UK to here, we're going to get X transpose K, KS transpose R, KS X of K. Right? Now, R is positive definite, so I can deconstruct X or R into this combination here. And then it's because of that, combining these three terms, we get this one here. And then the rest of the terms is the transpose of this term. Everyone sees that? Okay? This is a sort of a classical way to massage this cost function. So as you do some more examples, you will get very familiar with this. Okay, so now we have explained x of k, the dynamics of x of k is this one, right? This is the closed loop dynamics of x of k. If I just give you this equation here and I ask you, what's the mathematical solution for x of k? If I just give you this one, I give you the initial condition, I give you this dynamics of x of k. What's the solution? This is a review of ME 232. So the question is, let's say, take one more simple example. If, let's say, xk plus 1 is 2xk, initial condition is x0, what's the mathematical formula for xk? 2 power of k times x of 0. Right? Yeah, that's what I was asking. So if I give you this, what are the solutions for x? So the solution for x of k is this. For this general equation here, xk equals a CL k x of 0. Okay? So do this step. After you obtain this, substitute x of k as the solution here. Then you get this. Now, the summation is over k, so it doesn't depend on x of 0. I can take this one out, and I can take this one out. So I'm going to get this. Okay? So if you recall, this matrix, this WCL matrix, which equals to, from the definition here, 0, summation from 0 to infinity, ACL K transpose C R KS. So I'm going to ask you the question once I finish writing. What is this matrix WCL? PS. That is correct. You will notice this one. WCL is going to be PS. There is another side of this story here. This matrix is also the observability grammar of this matrix here, of the system here. All right? That is something kind of very interesting. So we have translated the performance index relating to the observability grammar of some new, this is the closed loop, new closed loop systems. Okay? Now, if the original system is observable, what do you think this one will be? This new system will be? Guess. If AC is observable, have a guess. What will this one look like? The conclusion is correct, but the analysis is a little bit not rigorous. So someone said it's going to be observable because it contains a C. Partially correct. Maybe if the score is 10, I will give you 3 to 4 points. Anyone wants to take another look? Full rank of what? If we constructed the observability matrix, it's going to be full rank. That's what you imply. So if we want to test the observability, we have several ways. We can construct the observability matrix, right? And then check the rank. That's one way to do. Okay? I want to show you that this is actually makes sense without going to the observability matrix construction. Okay. The first thing to look at is this. Maybe this is the first thing to look at. If the original system, AC, is observable, I just do one more step and construct this system. Think about it. This system has to be observable because the state dynamics are exactly the same. I'm just adding one output. I'm just adding an extra output over here, right? You notice everything else is the same. It's the original system. I'm just adding one output. So if I can already observe the states from this output alone, if I add one more, I will definitely be able to observe the states. So if AC is observable, then this guy has to be observable. Now, I was asking the observability of this guy here, which is the same output, but the state dynamics is a little bit different. But it doesn't matter because this one is the closed loop system of this guy under a feedback control law. So if you notice, if I substitute U here as a, let's say, as some kind of feedback dynamics, I'm going to feedback the output y tilde here. So let's see, what will be the feedback gain here? I look at this, so I see I need to some terms that contains k of s to make this happen. And this guy doesn't contain c. So I'm guessing the first one has to be c, has to be 0, and the second one has to be negative r negative 1 divided by 2. Let's see if that works. Okay? So if I substitute this is the static output feedback control law to this open loop system, then I'm going to get AXK plus BUK, but there's a minus sign. It's going to be minus B R negative 1 divided by 2 times this element here. So it's going to be KS X of K. So you see, this system is nothing but this open loop system controlled under static output feedback law, right? You can do this again and again. Look at this long enough, you will buy this. So if you recall, observability is invariant under static output feedback law. That's because if I see, it's again this analogy, if I can see the states from the output, then no matter how I massage the output into the system, I will still be able to see the states. Okay? So that's this picture here. Now, if this is observable, what will the observability Gramian be? Positive definite, right? So that means this. That means this matrix WCL is positive definite. That means PS is positive definite. Okay? So take a look at this again and try to have a quick memory of this. AC controllable or stabilizable means the Riccati equation is going to converge to a bounded steady state. And then if we have additionally the observability condition, then this one will be positive definite. The reason why we need this positive definite matrix, think about, for example, Lyapunov analysis. In Lyapunov analysis, we have a P matrix, right, which occurs in the V function, Lyapunov candidate function. We want that matrix to be positive definite, right? Just basic Lyapunov analysis. Now, P. We want this one to be positive definite. And this is exactly what we have done here. Okay? And if this happens with certain additional conditions, you can guess the closed loop system is going to be stable, right? Because we can find a valid Lyapunov equation. So coming back to the first two statements are the tool sets to conclude the closed loop stability of the system over here. Okay? Let's see. I'll start by recalling this algebraic Riccati equation over here. I mentioned to you that if you look at this, this is sort of like a quadratic function of P. Okay? And it looks actually very much alike a Lyapunov equation. If you recall standard Lyapunov equation, what's over there? PS equals A transpose PS A plus Q. This is sort of a standard Lyapunov equation. And we just have some extra term over here. And my next purpose is to explain to you how this guy can be sort of massaged into this Lyapunov equation. And then if I can do that, and then I found this guy is positive definite, that means I have a valid Lyapunov equation to conclude the closed loop stability. Okay? Let me ask you one more question. If I want to conclude the closed loop stability, what should be, my notation is a little bit, if I want to conclude the closed loop stability, what should be my matrix A here? I intentionally said it's A tilde to let you not think it's this matrix. It's something else. If I want to conclude closed loop stability. It's going to be the closed loop A matrix, right? It's this one, so which equals A minus BKS. So the next step, if you see that, then the next step here is doing nothing but it's sort of like add and subtract terms. This is my goal. I want to, in the end, arrive at something that looks like this. All right, you see the structure here. PS, A, transpose PS, and then something else. Okay? This is, we're going to talk about this detailed math later. But if you see that we can arrive this, and we have shown PS is positive definite. Then what does that mean? From this Lyapunov equation. This guy, this matrix here, is always positive semi-definite, right? So that means in this Lyapunov equation, we have found something that's positive semi-definite, and this is positive definite. That means the system is at least stable in the sense of Lyapunov, right? So after a few more algebra, the system turns out to be even asymptotically stable. But that's the big picture. And details, you can read back in the notes. These details are doing nothing but, first of all, I want something, in the goal, I want something Ks transpose Ps Kx. So I have to somehow generate a quadratic term of Kx. This is what's happening here. So from the first step to the second step, I'm adding and subtracting this term here. Not adding and subtracting, but adding this guy and the inverse of this guy to make it happen, to make this term occur twice. Okay? And then from here to here, I'm just constructing this one. I'm just trying to see what will make out this one. So I first constructed this, and then I add and subtract terms to make it equal to what I had. Okay? So these mathematical details, it's enough. You have seen it once and know how it works. But probably, yeah, let me finish. Probably you won't encounter this kind of situations in homeworks or something. Yeah.
For the conclusion, here you conclude that PS is positive definite, or your assumption was PS is positive definite, and then you go forward proving stability.
From here, PS is positive definite. That comes from our previous analysis that AC is observable. From here, what I have done is massaging this algebraic Riccati equation to a Lyapunov-like equation. So if I do that, then I can show the stability conditions for the closed-loop system.
So I think you should accept the condition. We know PS is positive definite.
Yes.
So this term is obvious that it's positive definite because PS is positive definite.
Yeah, you're commenting on this one?
No, on the above sentence, above that, this term here.
Yeah, yeah.
This term. Here, we know the first term is positive definite for sure, because we assume PS is positive definite.
Mm-hmm.
PS is positive definite. Also, the second term is positive definite.
You mean this term?
Yeah, this term is positive definite.
Positive semi-definite.
Positive semi-definite, positive semi-definite. Also, the first term is positive definite.
You said this is also positive definite.
Yeah.
Not quite. This one is positive semi-definite.
R could be zero.
R cannot be zero. R has to be positive definite.
So this term is positive definite.
No, this one still can be positive semi-definite. Think about this. I'll give you one example.
KS could be zero.
Because KS can mess up things. Yeah.
Yes. What's your conclusion here?
My conclusion is now I have found the Lyapunov equation for this closed-loop system. Right? This Lyapunov equation is about this closed-loop A matrix here. Right?
Okay.
So I found the Lyapunov equation, and I have shown for this positive semi-definite matrix, I have found a positive definite P. That means the closed loop is at least stable in the sense of Lyapunov. Yes?
So if we have a Lyapunov function and we find a solution that is positive definite, that means that it is stable. But then wasn't the other condition was that P is unique?
Oh, the other condition is if for Q, if for this one is positive definite and P is positive definite, that means the system is asymptotically stable.
But doesn't P have to be the unique and one and only solution to the Lyapunov function for that?
It requires a little. This thing is a little bit subtle. So think about a standard Lyapunov equation. I'll just say. the solution of P, if you see this, depends on Q. So if I have Q, if I have one Q that give me one P, and I can easily construct another Q, I can scale it, then I will have another P, right? So the uniqueness is not the dominating factor here. Yeah. So what's remaining to be done? I've shown the system is stable in the sense of Lyapunov. I have to somehow conclude it's asymptotically stable. Okay? That's one more step. And I will show you this powerful theorem. Okay? It turns out this is something that's used in a lot of places. Okay, so I think it's good to know. But it somehow was not mentioned in ME232, so I will summarize it here. This is an extension of Lyapunov theory based on observability. So it says this. If we find from Lyapunov equation, this is a standard Lyapunov equation, where P is positive definite, Q is positive semi-definite. And if we write Q as in this form, and AC is observable, it turns out that the system is asymptotically observable, or asymptotically stable. Okay? So this is exactly what I have just done. I have constructed a Lyapunov equation where this P matrix is positive definite, and this Q matrix, if you recall, is positive semi-definite, as written down here. But we have shown that this system is observable. So immediately we can apply this theorem to say the closed-loop system is asymptotically stable. Okay? So let's see. How many slides more? Let's do this. We can come back to the proof of this part, this theorem, if we have time. For the moment, the proof is actually not very difficult at all. And you will be it's easily understandable. If we have time, we're going to go back to this. Now, I want to give you one example, okay, to see why this all makes sense. So I have this first-order system over here, written down over here. Xk plus 1 equals 2xk plus uk. Is this system stable? This one? Not stable, right? Okay, we will use this. That's just an observation. So let's say if I choose Q and R in my performance index as 0 and 1, these are all valid, right? Because R is positive definite, Q is positive semi-definite. Okay, these are all valid assumptions. What do you think if I'm minimizing? What do you think? What's the optimal control law? Let's say summation from 0 to infinity, xk transpose q xk plus u transpose k r uk. What do you think is the optimal control law? If q is 0, this guy goes to 0. What's the optimal control law? U has to be 0, right? That's the way to minimize this. Okay? So that means we are doing nothing. We're not doing nothing. We are not doing anything to the system. And the reason for that is, again, okay, if this is 0, it's sort of like if I define Q equals C transpose C and Y equals CX, it's sort of like from this output, we cannot tell anything of the states because this guy is 0. Okay? So if we can't tell anything from the states, then there's nothing we can do this minimization here. So you see, the optimal control is 0. So if that happens, you see, the closed-loop system is not stable. Right? What conditions are failing here? I have explained that if some conditions hold, the closed-loop system is guaranteed to be stable. What conditions are not correct here? You see immediately, right? Is the system controllable? Yes, right? Because A is 2, B is 1. The system definitely controllable. So the observability condition is failing here. And as a result, the closed loop system is unstable. Okay? So hope this this convinces you that these conditions are good. These conditions are required to have a meaningful solution. Okay? So these are additional summaries. This slide, I just want to show you LQ problems. Steady-state LQ problems have excellent closed-loop properties. I have shown you in a little bit detailed equations. It has guaranteed closed-loop stability. Okay? But from ME232, if you read the notes over there, you will see it has excellent margins for single input systems. We have these margins over here. And then we have guaranteed stability for loop gain changes. Okay? So this is just showing excellent closed-loop properties. LQ is good in this sense. Okay? The details are, you can review it in the ME232 class reader. So as a summary, someone is still taking notes? Okay. As a summary, think what we have done for up till now for the class. We have reviewed the general discrete-time LQ problem. And then from here, we did a double integrator example. This is to show you that P, K converges to a steady state solution. But I was hiding this information here that double integrators are controllable and observable. That's why it happens. Okay? And then later, I showed you why, when this is guaranteed. So now you have seen AB, controllable or detectable. So, and then over here, later we showed its properties. So if adding the AC observability conditions, we can show it has excellent properties. Okay? So this is a quick summary of a discrete-time LQ problem. Okay, any questions for this part? So as you take some time to digest, start to introduce the next topic of some review of probability theory. Okay. First of all, what do you think? What do you think? Why we are learning this? Why these things can have potential usage for the class? Probability theory. By this I mean, think about the connections to control system design. Noise, exactly. So in previous studies, we have been focusing on this one. So we are pretty comfortable of designing control laws for this kind of systems. Okay, we can do, for example, state feedback for controllable systems. We can do output feedback. Okay. In practice, noises always occur, especially for practical systems, practical mechanical systems. Noises will enter into the system. Not just from the state dynamics, but also possibly from the output dynamics. Let me use VK here. So this is slightly more practical for practical system analysis. Okay? We have to know how to handle them. These things are sort of like, I don't know exactly how these gonna go. These are random. But I have some rough idea. By rough idea, I mean I can know how on average it behaves. I can know the mean of these noises. I can know the variance of the noises. So how can we do this control design problem by knowing just partial information of the noises here? Is what we're going to do. Is what we're going to do a few more lectures later. But first of all, we got to be able to understand how to analyze these noises above all. Okay? So I want to start by just looking at a very simple example. that we can think of. Say I'm throwing a dice, a failed dice, has 6 faces. Okay, 1, 2, 3, 4, 6. On each face has a number. Okay. This thing, you can see that the output, the outcome of throwing a dice depends on chance. It's random, right? So more in a more professional language, this is what we call them. So we say an experiment, such as one like this, is a situation whose outcome depends on chance. Okay? And each time we throw a dice, we call it one trail. Okay? So each time we perform an experiment, we call that it's a one trail. So a sample space, in this case, is a summary of all the possible outcomes. What will be, for example, what will be the sample space for throwing a failed dice? So either I get a 1, get a 2, 3, 4, 5, 6. So that's the sample space over there, right? So probability is just a discussion of how likely these things or events happen, all right? So I mentioned sort of a more professional way to say this is an event. An event is called, it contains some outcomes of the sample space. For example, if I throw a dice, an event can be I get an odd number from the output, or I get an even number from the output, or I get a 10 from the output, which has a probability of 0. Okay? So an event is just you see here, this is what I discussed. Event can contain one outcome. For example, the event of getting an A, getting a 1. The event can also contain non-outcomes. For example, getting a 0 from a failed dice. That's impossible to happen. But that's an event. Okay? Usually, when we do this sample space definition, we do this way. Omega equals small omega 1, small omega 2. Okay? So each small omega 1 defines a possible outcome. Random variable is simply the most important concept to start with analyzing probability and statistics. Okay, so the reason why we introduce random variables is we got to somehow be able to mathematically evaluate how likely things are going to happen. Okay, so a random variable is a real valued function. Okay, it's a function. It's going to map the cases, different outcomes, into some values. Okay? It's a real valued function defined on the sample space with this cumulative distribution function. Okay? So if we can say the random variable is less than something, we give it a mathematic evaluation of this probability. We define this as CDF, cumulative distribution function. Okay? It's just a intuitive properties of this cumulative distribution function. The probability of something cannot be negative. It has to be between 0 and 1. If the probability of something is 0, it means it's impossible to happen. For example, I'm going to have the final tomorrow for ME 232. Impossible to happen. But the cumulative distribution function probability, maximum probability is 1, which means this thing is definitely going to happen. Okay? Let's do one example. This definition of random variable is actually contains a rich field of results that's going to be very, very useful. So first one is this. When we throw a failed dice, I can very easily, this is the most intuitive one, I can define the random variable as this. It's going to map each case, each outcome to a number like this. If I'm getting a 1 from this failed dice, I say this random variable is mapping this outcome to be 1, 2. This is I get a 2 from throwing this failed dice. But I can also, this is another definition of a random variable. I can define this random variable as the indicator of whether the obtained number is even, okay? Then in this case, different outcomes are mapped into totally different numbers, you see? The indicator, if I throw a failed dice and I get the outcome of 1, then this random variable is 0 because it's not even, so this indicator is 0. If I'm getting 2 or 4 or 6, then the indicator is 1, okay? So a sort of take-home message is this. For the same sample space, I'm just throwing a failed dice. I can define totally different random variables, right? This will be sort of useful in future analysis. Okay? We have defined probability CDF, cumulative distribution function, as a sort of additional add-on feature, not add-on feature, this one is important itself. So this probability density function is, for the continuous time case, is the derivative of the CDF, okay? And because of this definition here, if I want to evaluate the probability of a random variable to fall into some sort of regions, we can do this integration. Now you see, we're immediately using the random variable definitions, all right? If this is a random variable, it's some values, okay? It's mapping some outcomes in reality into some values. So that's why we can do this. So we can do this random variable falls into some mathematical regions over here and evaluate the probability, which is the integral here, okay? Sometimes instead of writing this one, we write Px of x, just to emphasize that this is describing the properties of the random variable x. Okay? Usually, for random variable, we most commonly evaluate two things. First of all, the mean, how it behaves on average. This is the definition. Expected value E of x is defined as how this integral here, how this random variable x behaves overall, the average behavior. And then this, because of this here, this is sort of like, because of this, this integral, the form of the integral here, this is usually called the first moment of this random variable. So going from here to sort of like a second quadratic function here, this is the second moment of the random variable, which is the variance. So the variance is describing how a random variable, the possibility of variations around its mean value. Okay, so it's this one. It's sort of like a second order property of the random variable. Okay, so some more definitions which you must be very familiar with is the standard deviation, which is the square root. Yes.
Max, I was just wondering if in these slides you use the notation that capital letters mean the random variable itself and lowercase letters mean the value of the random variable.
Correct. Okay. Yeah. So exactly. So capital letters means random variable. X, it's some values. Yeah. Okay. Standard deviations. Let's see. This is almost considered as a fact when doing probability analysis. The variance of x, you can compute it from this definition here. You can also compute it from this property here. It's expected value of x squared minus the square value of this expected value of x. Okay? So you can verify this. This is actually not very difficult to verify. Everyone comfortable with the pace of the review? Okay. Let me know if you think this is too fast or too slow. Okay, example distributions. There are a fair amount of distributions that are important, useful in practice. The first one is the easiest one. It's the uniform distribution. Uniform distribution means the random variable can take values uniformly possible with uniform possibilities in some region from x min to x max, okay? With the probability density function of this 1 divided by x max minus x min, okay? And the cumulative distribution function you can obtain from the integral of this one to obtain this one. I wanna do a quick check of this final result here, and I want to tell you that these are very intuitive results. So you can, the first one is very intuitive. The mean of a uniform distribution, uniformly distributed random variable is the middle point here, right? If it's uniformly possible distributed in this, the mean value is here. This variance function, this equation for the variance is this one. It's a squared of the length of this region divided by some numbers. Okay? If you think about it, I just told you the variance is sort of a second order property, right? It's defined by integration of x minus mean of x squared pxx dx. Okay? It's a second order property. So that's why it has a squared term. Okay? And as you can see, the larger these regions are, the larger these possible regions for the random variable to occur, the larger variance it can be, it will be, right? Some intuitions to understand this result here. And this scalar, this is a normalization scalar. This is just for making sure the cumulative distribution function in the end, it's going to be 1 for x, for all the possible x. Okay? Another one that's very, very important. I would say this is simply the most important random distribution for ME233. It's a Gaussian, or sometimes known as a normal distribution. Okay? A Gaussian distribution, the PDF looks like this. It looks like a little mountain over here. And the mean is the peak of the mountain. And the variation, the variance, the standard deviation is the length of this region. Okay? So sometimes this is 1 sigma value. This is 1 standard deviation value. So in a lot of engineering applications, we would say 1 sigma, 2 sigma, 3 sigma. Sometimes in a lot of engineering practices, this 3 sigma value defines a lot of things. So you see, for the range covered in these 3 sigma regions, you see, the majority of the cases, the majority of the values happen here. So it's very likely the random variable is going to fall into this region. Sometimes people even use 6 sigma values, okay, which is even far, far away from here. Okay, the mathematic description of the PDF for a Gaussian distribution is this. It's an exponential function. It's described like this. Okay, so it contains. Look at this one. It's defined by mean value and the standard deviation value. Nothing else. Okay? So because of this fact, because PDF is fully characterized by M of x and sigma x, so a normal distribution, it's usually denoted as this. Normal distribution with mean and standard deviation. Okay? The main purpose, I explained this is simply the most important distribution in 233, is because of this. This central limit theory. So it says for large collection of independent random variables. If we sum them up, if we sum them up, remove the average. If we sum them up, as long as there are sufficiently a large amount of independent random variables, then the behavior of this summation new random variable is a normal distribution. Okay? So it's saying, in practice, if I have a lot of randomness, independent randomness in practice, then the overall behavior looks like a Gaussian. Okay? So notice here, when I say x1, x2, x3, I say they are independent, identically distributed. I didn't say anything about whether this is normal, this is Gaussian, or this is other kind of distribution. I didn't say anything about that. That's the power of this. Regardless of how these individual distributions are, as long as they are independent, identically distributed, this guy is Gaussian, converges to a Gaussian. That's a very powerful result if you think about it. Okay? So as an example, as a mathematical example, let's take a look at this case. So if you can see the MATLAB commands here. So I have first generated 3 uniform distributed random variables using rand. This is the command in MATLAB. Okay? And then I sum up the first 2. And then I plot how this z behaves like. This is the result. So if I sum up 2 uniformly distributed random variables, this is how the summation new random variable looks like, the distribution. Now, if I sum up 3, and I plot it again, so this one is for this one, and I plot it again, looks like this. This looks familiar? The mountain shape looks like a Gaussian, right? So I've just done 3 cases here. Imagine I'm summing a lot of terms. Then this mountain shape will become more and more evident.
Here, what do you mean by identical distributed?
It means, in everyday language, it means this guy just does his own things, and this guy does his own things. These two, it's like totally in 2 different worlds.
So they're independent, you mean?
Yeah.
So the actually independent identically means independent.
Identically has sort of another layer of meanings. Yeah. Let's see. Independent.
Max, does it mean that the underlying distribution for each xn is the same?
Not. I think it's right, but at the moment I do not have there's not one click that I can guarantee you that's the case. But you can look it up. Identically distributed. Probably yes, you're right. Okay, so we have discussed a random variable and some individual distributions of random variables. But in practice, we have to sort of usually evaluate this joint probability, which means one thing can be random, and there can be another thing that's random. And these 2 random things, they can interact, they may not be interacting. But these 2 things, multiple randomness can enter into a system. So that's why we need joint probability. Okay? I have shown you for same sample space, multiple random variables can be defined. So let's say x is one random variable and y is one random variable. So it makes sense to evaluate this. The probability of one of them equals some number, and the probability of the other equals some other numbers. So it also makes sense to define the joint cumulative distribution function as this guy. What's the probability of these guys, x is less than or equal to small x, and y less than or equal to small y, okay? Then joint probability density function, which is this partial derivative with respect to x and y. Now, this one is new, covariance, which is sort of evaluating how these two is interacting, okay? So covariance is defined by the expected value of x minus the mean of x, y minus the mean of y, okay? So from here, this is the mathematical evaluation of the covariance. It's the double integration of this thing here, okay? If you evaluate this one, if you evaluate this guy, you can obtain this. This is this equation is often used as a evaluation of the covariance between x and y, okay? So this can be very easily done by using this definition of the covariance, okay? Just to write down the full, just to expand this term, then you will be able to see this one, okay? So from here, the covariance definition, if the covariance of two random variables is zero, then we say the two random variables are uncorrelated, okay? Independent, we mentioned independent from the central limit theorem. So two independent random variables, they satisfy this. So basically it's saying they live in different worlds. So the probability of x and y, joint probability, is going to be, you can simply do the product of each term, okay? So this is from the viewpoint of PDF. From the viewpoint of CDF, you have this. The probability of each one of them falling into some regions is nothing but the two individual probabilities multiplied together, okay? Independence. So definitions of joint probability. Here. So if you recall what we did, we discussed uncorrelated, okay? We said two random variables are uncorrelated if their covariance is zero. I always find it more convenient to define uncorrelation this way, because covariance and correlation, these two concepts sounds confusing starting at the beginning. Later, it will clear out. But there's another definition of uncorrelated, which is more intuitive in my, I think, all right? So there's this definition of correlation coefficient, which is defined as rho xy, which is the covariance of xy divided by the variance of each term, which divided by the standard deviation of each term over here. And then uncorrelated means the correlation coefficient is zero, okay? So I think this sense, the definition has no confusing part over here. If the correlation coefficient is zero, then they are uncorrelated, okay? As a remark, if two random variables are independent, they are uncorrelated. This is intuitive. If these two are happening in different worlds, then they are not correlated. But not correlated doesn't mean they are independent, just as a checkpoint. This is because of this. So the covariance, which is expected value of x minus m of x, y minus m of y, is this one. We have introduced this equation here. The covariance being zero, you see, is just about the mean of something being zero, right? As you can imagine, the mean is, I mentioned, this is just the first moment, the first order property of a random variable. But a full picture of a random variable is the PDF, right? Or CDF. So you see, using this property of the mean of something is definitely weaker than talking about the independence, the actual PDF of two random variables. Okay? So independent, uncorrelated, but uncorrelated doesn't mean independent. I have one example here, which you can take a look. This example is sort of, when you read it, you see it intuitively makes sense. But if someone asks you to construct one example like that, it's very difficult. Okay. Let's see. I'll talk a little bit more about multiple random variables. Then we'll end up today's lecture. So I mentioned if I have two random variables, these two can interact with each other. So it's very convenient to define a random vector, which is a collection of random variables shown here. Okay? If I define this vector notation, I can say its mean is going to be a vector. And then the covariance matrix is going to be defined this way. So recall how we defined, for example, the variance of a single random variable. Let's say var x is defined by expected value of x minus mean of x squared. Okay? This is for a single random variable. For a random vector, we define, because now for a vector, dimensions are important. So for a random vector, we define the covariance matrix as this. Okay? This is a skinny matrix, and then this one, the transpose of it, is the wide matrix. Okay? So in the end, this whole thing is going to be a matrix. So in this case, it's going to be a 4x4 matrix. And over here, individual terms inside this matrix are defined by, this one is the variance of x, you see here. Sort of the variance of x over here. But because, excuse me, because this joint probability distribution, so in the end, it's timing this joint probability PDF function. Okay? Okay, so imagine you have two random variables. They are, let's say, they are dependent on each other. But you want to find this. You want to find how a single random variable is behaving from this joint PDF. Then the thing to do is to integrate out the randomness of y. Okay? So this is how you can obtain a single PDF from a joint PDF. And I have been mentioning this for a couple of times, that when two random variables exist, they can interact with each other, which means they have correlations. And because of that, one variable can have certain kind of dependence on each other. So it's meaningful to define a conditional probability distribution function. So the notation is like, what's the probability of x if I give you a value of y like this? Okay? So it's the probability of x given y equals y1. It's defined by this one. So it's the probability, it's the joint probability divided by the single PDF of y. This one is kind of makes sense from the control system point of view. So recall a control system. Let's say just this one. I don't have an input. You will see that this is useful because we can only measure y. Oh, I have to put noise here. We can only measure y. We cannot measure x. So if I give you one measurement of y, then we can sort of infer the statistical properties of x, right? So this is why this is useful. And as a matter of fact, this is going to be extremely important for a state estimation series. So this is conditional PDF. So following this conditional PDF, we can immediately define the conditional mean, which is how on average X will behave if I give you one measurement of Y. So it's the integration of the conditional PDF over here, in product with the value of X. Okay? As a matter of fact, let's try to see more details of this conditional PDF. What will happen if X and Y are totally independent? What will this guy be? If they're totally independent, I give you a value of Y1. I give you something in another world. We cannot infer anything in this world here. So if they're totally independent, then this will happen. Okay? This can be evaluated from here. If they're totally independent, then Pxy equals, so now it's convenient to put notation like this. Right? Now they're going to cancel because this guy is the direct product. So that's how it's actually evaluated. So independent means this. Okay? This property is kind of very useful. So when I say the expected value of X given Y, what do you think this guy is going to be a function of? So the information of X is averaged out. And the information that's feeding, this value here is going to depend on what kind of Y I give you, right? The information of X from here has been averaged out from this integral. So you see here, this guy is going to be dependent on Y1. So here, this guy is going to be a function of Y. If Y is random itself, then this will be a random variable, depending on Y. Now, if I take one more expectation with respect to Y, you can verify this, that this thing equals expected value of X. So if you average out the information of X in the first step, then you average out the information of Y in the second step, then you get the average behavior of X. So you can verify this. This is extremely useful, actually. Okay? We won't have time to verify this. Hopefully you can have some exercise in the homework. Okay, so I think I will stop here. And then in the next lectures, I will extensively talk about what will happen if X and Y are Gaussian. Okay? All right. See you next week.